So far, we've considered states of multiple particles, presuming those particles interact sufficiently weakly that we can write the wave functions approximately as products of the wave functions of the individual particles considered on their own. Generally, however, we cannot factor multiple particle states this way. How then can we deal with strong interaction between the particles and yet still handle the symmetries of the wave function with respect to exchange? The answer is to construct basis functions for the direct product space corresponding to the multiple particle system in which all of those basis functions possess the required symmetries with respect to exchange. If each basis function has the required symmetry with respect to exchange, then any linear combination representing the state of the possibly interacting multiple particle system will also have the same symmetry properties with respect to exchange. So let's see how this works. So we can find some complete basis set to represent one of the particles, whatever basis we like that is good for representing, say, an electron or a proton or something like that. And we have used J here to be indexing what particle we're talking about, and I is indexing the state that the particle could be in, the single particle state or possibly the mode. And then we can formally construct a new basis set for the multiple particle system using these basis functions for single particles. And then we will have some n-particle system basis functions. In these different basis functions, these A's and B's and so on could refer to different single particle states or modes. So one set, this A, might be the lowest state of a particle in a potential well, for example. In another one of the basis functions, it might be the second state, for example. So these basis functions are going to be formed using products of single particle basis functions that each correspond to one particle being in a specific one of these basis states. But of course, this entire basis function has to be appropriately symmetrized with respect to exchange to correspond to whatever class of particles we're talking about, such as non-identical particles or bosons or fermions. So, depending on the symmetry with respect to exchange, there are different forms for this basis function. For non-identical particles, it's straightforward. One particular basis function for these capital N particles here would be particle 1 in some state A, particle 2 in some state B, and so on. And these states could be any of the allowed single particle basis functions for this class of particle. So this might be some electron in the lowest state of a potential well. This might be a proton in the second state of some other system. Equivalently, we could write this in Dirac notation like we've been using so far. This basis function, which we've just written as an ordinary product here, would be the product of these kets. So as I said, each one of these psi A of R may be chosen to be any of the single particle basis functions for this system, since these are non-identical particles and there's no Pauli exclusion and there's no requirement for symmetrizing with respect to exchange. For identical bosons, the basis state would take this form, where A and B and so on were specific basis states for the single particle states, or modes we would usually call them with bosons. So different ones of these basis functions would have different lists of these basis functions for the single particle states or modes in here. But the form of any one of them would be like this, as we've discussed before with these permutation operators here. And for identical fermions, we could similarly form basis functions for the n-particle system just using these kinds of lists that we've looked at already. And again, different ones of these multiple particle basis functions would have different A's and B's and so on corresponding to the single particle states. And of course, with the fermions, all of these states have to be different states. So, for non-identical particles, there is one basis function for every choice of combination of single particle basis functions. if we imagined that there were m possible single particle basis functions, such as, say, the first m levels in some potential well, somehow those were the only ones we had to consider here, and we presumed there were n particles, then there are in general m to the power n such basis functions for the n particle system, because for each particle we can choose to put it in any one of the n states. So, for n non-identical particles, specifying a state of that n-particle system involves specifying a linear combination of the m to the power n different orthogonal n-particle basis functions. Because there are only m to the power n different orthogonal n-particle basis functions, there can only be m to the power n different orthogonal n-particle states, even if we allow the particles to interact. So the states when the particles are interacting will not in general be the basis states, they'll be linear combinations of them. But there can't be more orthogonal linear combinations than there are orthogonal basis states to start with. So, as we said, because there are only m to the power n different orthogonal n-particle basis functions, there can only be m to the power n different orthogonal n-particle states, even allowing the particles to interact. So, to repeat, for n non-identical particles, even allowing them to interact, there are only m to the power n possible orthogonal n-particle states, each of which will be a different combination of the m to the power n different n-particle basis functions. So the total number of orthogonal states of n non-identical particles with m available single particle states or modes is m to the power n, which of course has to be equal to the total number of orthogonal basis functions for this n particle system, in this case with m available single particle states or modes. In the case of identical bosons, the n-particle basis states, corresponding to different permutations of the same set of choices of basis modes, are not distinct. And so there are fewer basis states in this case of identical bosons than there are for non-identical particles. For example, we see that in this basis state here, for n identical bosons, this state with A, B all the way up to n is not distinct from this state with B, A all the way up to n. Since all the permutations of the products of the basis modes are already in the sum, these two states are the same sum of products performed in a different order. So, because these two states are not distinct, there are fewer orthogonal distinct basis states for identical bosons than there are for non-identical particles. The counting of these boson states is complicated, but it corresponds to a standard result in permutations and combinations, which is the problem of counting the number of combinations of n things, here the single particle states or modes, taken n at a time, since we always have n particles, with repetitions allowed. That is, we can have more than one particle in a mode. And we get, therefore, this standard result from the theory of permutations and combinations, that this number of distinct basis functions for bosons, where we have n particles and m possible modes, is m plus n minus 1 factorial over n factorial into m minus 1 factorial. So we're not going to prove that result here. It's a standard result in permutations and combinations, but it takes a little bit of work to prove it. For example, think of m boxes, each containing as many blocks as we like of just one color, with each box containing a different color of blocks. We are picking n blocks altogether from these boxes, and the number of possible different combinations of blocks we can end up with is this formula we wrote down. So that's the problem when described in a form that is similar to how we would think about permutations and combinations generally. For example, the set of combinations of 2 particles, that's n equals 2, among 3 modes, that's m equals 3, so these modes will label A, B, and C, and we allow repetitions, is AB, so that's 1 particle in state A, 1 particle in state B, AC, BC, AA, that is both particles in state or mode A, BB, both particles in state or mode B, and CC similarly. And that gives 6 in all, and that does indeed correspond to the result we would get from that formula, m plus n minus 1 over n factorial into m minus 1 factorial, and that is 6, which you can check. Just as for the non-identical particle case, this number of basis states is also the number of different orthogonal states we can have for the same reasoning for this set of identical boson particles, even if we allow them to interact. And so, for our n identical bosons with m available modes for the bosons, the number of orthogonal states of those n identical bosons is then given by this formula that we just wrote down. In the case of identical fermions, just as in the identical boson case, we avoid double counting permutations of the same choice of single particle basis states. Additionally, many of these basis functions would not exist because they would involve more than one particle in the same single particle state. So there are even fewer possible basis states for multiple identical fermions. Specifically for fermions, if there are m choices for the first basis single particle state A in this overall n particle basis state, then there are m minus 1 choices for the second single particle basis state B, because we can't put 2 fermions in the same state, and so on down to m minus n plus 1 choices for the last single particle basis state n. Hence, instead of m to the n initial choices, we have only this number of initial choices. And the order of the choice of the states does not matter here because the particles are identical. And so we divide by the number of the different orders we have. We divide by n factorial. Hence, in the identical fermion case, there are m factorial over m minus n factorial possible basis states. And hence, by the same reasoning as before, the same number of possible orthogonal n identical fermion states altogether when we have m possible single particle states to choose from. And this is true even if we allow interactions between the particles. So, the number of orthogonal states of n identical fermions with m available single particle states is given by this expression.